Hi and welcome back to another LeetCode video. Today we're looking at LeetCode 3350, adjacent increasing subarray detection 2. It's a medium problem. Which topics is it? Tell us. Array, binary search, and contest. Okay, so this is actually quite an interesting one, and I want to show you how to solve it in linear time and constant space. So, yeah, what are we dealing with? Well, let's read the description. So we're given an array nums of n integers, and our task is to find the maximum value of k for which there exist two adjacent subarrays of length k, such that both subarrays are strictly increasing. Specifically, check if there are two subarrays of length k starting in indices a and b, where a is smaller than b, where both subarrays from a to a plus k minus 1 and the adjacent subarray from b to b plus k minus 1 are strictly increasing. The subarrays must be adjacent, and we should return the maximum value of k. And a subarray is a continuous non-empty sequence of elements with an array. Well, so what does that mean? Well, let's take this array here, for example. And let's put this on the drawing board. So what that means is we need to find two arrays that are adjacent to each other, or two subarrays that are adjacent to each other, where the elements in each of them are strictly increasing. So here you can see 2 goes to 5, that is increasing, 5 goes to 7, that's increasing, 7 to 8, and 8 to 9. All of those values are increasing. This would be one subarray of increasing adjacent numbers. And here you have, well, 2 increased 3, 3 to 4. So this is now another subarray that is strictly increasing, but it's of length 3. This is of length 5, right? 5, 3. And then here we have two other subarrays that only contain one element. And then these arrays are also strictly increasing, 1 and 1. Now we're looking for two adjacent subarrays that are strictly increasing. And we should return the max value of k for how many elements they have. And in this case, we have these two subarrays that are adjacent to each other and that are strictly increasing. So k will be 3 in our example. K will be 3. So let's go back to the code, and it's exactly that. Subarray starting at index 7, 8, and 9, 7, 8, and 9, and 2 and 3. Now, let's look at the second example, and we'll do the same thing. So we can see that here we have an strictly increasing subarray of length 4. We see that here we have another one that is increasing of length 4, but they're not adjacent, right? And all of these of length 1. But now, what we could also say is, wait a second, these are also two increasing subarrays that are adjacent to each other of length 2 each. So in this case, the result should be 2. So how can we approach this? Well, what if, when we iterate over an array and its values, what if we just count how many elements are in increasing order, right? So we know here we have 4, here we have 1, 1, and then we have here it's again 4. So if we knew only these numbers, these 4 numbers here, could we determine the result? Well, it turns out we actually can. So all we need to do now is we have to find two adjacent numbers and take their minimum. So we could say the minimum of these two numbers. Well, what is it? It's 1. The minimum of these two numbers is also 1. The minimum of these two is also 1. So that is the first way how we could determine a solution, and that would work in this example above here, where we have 2, 5, 7, 8. Here our numbers would be 2, 3, 4, 5. The next number would be 1, 2, 3. And then we had a 1 and a 1, right? So in this case, we would have this array to work with. And if we now take the minimum of each adjacent pair of numbers, so this would be 3, this would be 1, this would be 1, and the maximum is our result actually. That is actually the correct result. Now in this case, none of these ones are our result. So we also need to take into account each number divided by 2 is also a possible result, because any subarray with n numbers in increasing order can be split into 2 subarrays where you just do an n divided by 2, but an integer division. So in that case, the value would be 2 here. Here it would be 0, 0, and here 2. So we take the maximum now of all of these numbers, of these 2s, 0s, 1s, and that is our result. Yeah, so all we need to do to solve the problem is iterate through it, count how many numbers are increasing order and adjacent to each other. We could write all of that into an array, right? And then compute the result. Or we could directly just keep track of what was the previous array, and we could take the current count of increasing numbers, integer divided by 2, as a potential result. Right, so that is what we're going to do. And that will be O of n time and O of 1 space solution. If you wanted to store these numbers in an array, that would be O of n space, and that well, maybe we should do both implementations. How about that? Yeah, let's do both implementations. So the first one, O of n time and O of 1 space. So all we have to do is we have to have an array where we store all the counters, and we need to have a current count. We know that from the problem descriptions that we have at least 2 numbers in our array, and we'll initialize our count with 1, because if we have a sequence of numbers that are increasing, so if we find, we will always check 2 adjacent numbers. So our first check will be these 2 numbers. Then we increase the count by 1. But actually we already have 2 numbers now in increasing order, so that's why we initialize our counter with 1. Right. Okay, going to iterate over the indices numbers, and we're going to subtract 1 because we need adjacent numbers all the time. And now our check is if nums at position I larger or equal at nums at plus 1. That means, well, that means that our increasing sequence has been interrupted. Now what we just do is we just append to our counters array. Just append our count, set our count to 0, and then we start the new count. So when we find a break, so we are where the numbers are not increasing, for example, between 9 and 2, if I is pointing at the 9, then this will return true, this expression. We append the count of how many numbers we found in increasing order, and we will reset it to 0, but it's going to be starting at 1 immediately again at index I plus. Right, and now, well, what do we do now? Think. So we're going to append the count, and maybe for illustration purposes, I'm going to print this out. And we're going to say result equals 0, just a dummy, just so that we can see what we get in our counters array. So here we get our counters, 5 numbers in increasing order, then 3, and and outside the loop, we have to append the counters as well, right? So that was a mistake. Right, so now we have 5 through 3, exactly what we've seen before. So that is here 5, 3, 1, 1. Wait a second. Oh yeah, 5, 3, 1, 1. Okay. And in the second case, we have 4, 1, 1, 4, which was exactly what we had as well. 4, 1, 1, 4. Right. So now we just need to iterate over the array, and our potential result is either the number divided by 2 or the minimum between the current number and the next number. And the way to do that is simply just, so we say result is the maximum of all the counters, so of all the numbers in the array, integer divided by 2. And now we need to compare, you know, if we have two adjacent counters, maybe their minimum is larger than the maximum counter. Or I in range thing counters. One again, result is maximum between result and the minimum of counters at position I and counters at I plus. We just return the result. And so if I run this now, so both of the cases pass. If I submit this, see that it passes all of the tests. Right. So that is of and time of and space. You can think about, you know, if you want to know when you get the worst space, well, this is essentially when you have all same numbers in your array. Then you're always going to append a counter, and the length of your counter array is also going to be n, which is exactly the length of how many numbers you have. So how do we bring this down to a constant space now? Well, the trick is not to have the counters and to compute the result on the fly, right? Start with the result of 0. We still have all our count. But instead of appending the count, what we'll do is we will say result equals max result. And of course the count integer divided by 2. So that every time we do that, we need to do that. And actually we can do this right here. We don't have to do it just in this case. We can do it all the time. It doesn't matter. When the count gets larger, you know, at one point it will reach the maximum. We don't have to wait until we end of a subsequence. We can just take the maximum all the time. It's never going to be wrong. And well, the other thing we need to do is we need to, well, build the maximum between the result and the minimum of the current count and, well, a previous count, right? So that means we have to keep track of a previous count now. And we could say the previous count starts at 0, because initially we don't have a previous array or subarray. And every time we reset our count to 0, we just set the previous count to count. And that should take care of that. Right. So now we're not storing the counts in an array anymore. We're immediately using this to update our result variable. So if I run this now, it would also pass all of the test cases. And I can submit this as well. And voila, there we go. Actually slightly slower, interesting. Well, that's because we have more, we access more different variable sizes. Anyway, but the runtime complexity is the same, but we've now reduced it to an O of n space complexity. And that is how you solve that in linear time and constant space.